This is lecture number 17 of our course on fundamentals of transport processes. Welcome. We were going through viscous flows in the limit of low Reynolds numbers, where inertial effects are negligible, and so the inertial terms in the momentum conservation equation can be neglected. And I had shown you that for these flows, the conservation equations are mass conservation equation, the divergence of velocity is equal to 0, and the momentum conservation equation without the inertial terms. So, the divergence of the total stress is equal to 0, or minus partial p by partial xi. And the stress is given by Tij minus p delta ij plus mu times 2 mu times the symmetric part of the rate of deformation tensor. So, mu times partial ui by partial xj plus. And we had discussed a scheme for solving these equations. The first thing you do, you take the divergence of the momentum conservation equation, and you will get del square p is equal to 0. That is because when I take the divergence of the momentum conservation equation, the divergence of del square u is the same as the Laplacian of the divergence of u, which is 0. Okay. So, to solve the equation, first I solve for the pressure field, del square p is equal to 0, and then if you know the pressure, you can insert that into the momentum conservation equation to get an inhomogeneous equation for the velocity. So, you have an inhomogeneous equation for the velocity minus grad p plus mu del square u is equal to 0. The way to solve it is by separating out the velocity into a general solution plus a particular solution. The general solution is the solution of the homogeneous equation without the inhomogeneous part. So, for the general solution, the equation is del square u general is equal to 0. That is, the general solution satisfies the homogeneous equation without the pressure term. Okay. The particular solution is any one solution which satisfies the entire equation. You can choose any one, the one that is most convenient to you. The general solution contains the constants of integration, particular solution does not have to contain any. Okay. And we found one particular solution that satisfies this equation, and that is that the particular solution is equal to 1 by 2 mu p times xi. Okay. So, that was the particular solution, and this total solution ui is equal to ui general plus ui particular. So, that is the final solution that you get. So, for these viscous flows, the problem reduces to one of solving two Laplace equations, one for the scalar pressure and the other for the vector velocity. If you can solve these two Laplace equations and then put them in, okay, and then satisfy boundary conditions, you have the entire solution. So, that is the way that we will try to solve these equations. For definiteness, let us look at a specific problem, and that is of a sphere settling in a fluid. A sphere of some radius r settling in a fluid with some velocity capital U. And we want to find out what is the velocity field around the sphere and what is the net force exerted on the sphere due to the fluid around it. Since you have one sphere in a settling fluid and there is no other boundaries, it is most convenient to use a coordinate system whose center is at the center of the sphere. If you do that, the system is spherically symmetric, the configuration is spherically symmetric, the sphere velocity of course is not spherically symmetric, it is in one direction alone. So, let us choose a coordinate system which is centered at the center of the sphere. And as I told you, we shall solve this in vector notation without reference to the underlying coordinate system. So, I have to solve the Stokes equations for this case. Del dot u is equal to 0 minus grad p plus mu del square u is equal to 0 with the no slip condition on the surface of the sphere. No slip condition, the velocity of the fluid on the surface of the sphere is equal to the velocity of the sphere itself. Okay. So, at the surface, that is r is equal to capital R, the velocity of the fluid has to be equal to the velocity of the sphere itself. That is that the fluid velocity is equal to the sphere velocity. The sphere velocity is capital U as specified over here in one particular direction. Okay. We do not have to specify that direction beforehand, we will just assume that it is moving in one particular direction. So, we have to obtain solutions for the velocity field and the pressure field, Laplace equations for the pressure and for the general solution for the velocity field. Okay. So, we have to obtain solutions for del square p is equal to 0, del square u I general is equal to 0, put them both together and get the final solution, and then select the constants in that solution in order to satisfy the boundary condition. The way to obtain general solutions for the Laplace equation in terms of general scalars, vectors and tensors we had discussed in the last lecture. If you recall, in our previous course on fundamentals of transport processes 1, we had actually obtained the general solution for the Laplace equation in two ways. One was using separation of variables in the r theta phi coordinates, and in that case we got a solution in terms of the Legendre polynomials in the theta, in the azimuthal angle, and cos and sine in the meridional direction, and in the radial direction you had growing and decaying harmonics. The decaying harmonics decreased with r as 1 over r power n plus 1, the growing harmonics increased as r power plus n. Okay. So, we had solutions that were of the form a n m by r power n plus 1 plus b n m r power n p n m of cos theta times e power I m phi. Okay. So, that was one way that we had obtained for a particular case of a temperature field that satisfied the Laplace equation, where a n m and b n m are constants, and m goes from minus n to plus n, and n is equal to 0 to infinity. Okay. So, those were the solutions that we obtained by separation of variables techniques. We also obtained solutions by superposing sources and sinks. So, the first solution for n is equal to 0, 1 by r, was the solution due to a point source of heat. Okay. So, solution due to the point source of heat was equal to q by 4 pi k r plus T infinity. Okay. So, that was for a point source. Then if you superpose a source and a sink close to each other, you get a dipole, and the temperature field due to that decreases as 1 over r square. You get three such linearly independent solutions, one in which the source and sink are separated along the z axis, second along the x, and the third along the y axis. So, that gives you the dipole, and then you also get the quadrupole moments, in which you have two sources and two sinks in such a way that the net source is equal to 0, the net dipole is equal to 0, and you ended up with a quadrupole moment. So, those were two ways that we did in the course on fundamentals of transport processes 1. In this lecture, in the previous lecture in our present course, we had looked at another way of getting solutions which unified both of these. Okay. So, the way of getting the solution was to first take the solution for the source as the fundamental solution. Okay. We know that in a spherical coordinate system, if the solution is spherically symmetric, that is, there is no dependence on theta and phi coordinates, the equation, the Laplace equation, reduces to and that has a solution which to within an undetermined constant is just 1 over r. Okay. So, this satisfies phi naught, satisfies the equation del square phi naught is equal to 0. Okay. To get a vector solution, I take the gradient of this entire equation. Okay. I take the gradient of this entire equation. Okay. This is still equal to 0. Okay. If you take, if del square phi naught is equal to 0, its gradient is also equal to 0. Okay. Therefore, you get del square partial phi naught by partial x I is equal to 0, okay, just by interchanging the order of differentiation. So, obviously, the gradient of phi naught is also a solution of the Laplace equation, and that is a vector solution. It is the gradient of phi naught. So, it is a vector solution, and we had obtained that constant once again to within an undetermined constant as x I by r cubed. Okay. If you recall, when we did this, we used the identity that partial r by partial x I is equal to x I by r, okay, because r is equal to square root of x 1 square plus x 2 square plus x 3 square. Okay. And then to get the next solution, you can once again take the gradient of this vector, okay, take the gradient of this vector. So, partial by partial x j of del square phi 1 I is equal to 0. So, partial by partial x j of phi 1 I also satisfies the Laplace equation. Okay. Put an I here. Okay. Therefore, you get the second solution phi 2 I j is equal to delta I j by r cubed minus 3 perfect. Okay, this is a solution of the equation del square of partial by partial x j of phi 1 I is equal to 0. Okay. And then you can take one more gradient. So, this solution phi 2 is a second order tensor. Take one more gradient, you get a third order tensor, and so on. Okay. So, you can get an infinite series of solutions. Okay. As I showed you, this one, this first term here corresponds to a source. The second term is a dipole. The vector solution, it has 3 components, 3 solutions where the dipoles are arranged along the x, y and z axis, or the x 1, x 2 and x 3 axis. The next, the second order tensor solution is a quadrupole. It is symmetric and traceless, as I showed you, because the trace of the second order tensor is just del square of phi naught, which has to be 0. Symmetric and traceless, it has 5 independent components, and therefore, it exactly corresponds to the 5 components of this solution for n is equal to 2 and m is equal to minus 2, minus 1, 0, plus 1 and plus 2. So, these were the solutions that were obtained by taking successive gradients of that scalar source solutions. These are the decaying harmonics. The source decreases as 1 over r, the dipole solution decreases as 1 over r square, x I by r cubed. So, x I is x 1, which is r sin theta cos phi, x 2 is r sin theta sin phi, and x 3 is r cos theta, divided by r cubed gives me 1 over r square. Physically, it is clear. Every time you take a gradient, the dimension has to go as length inverse times the previous one, okay, because the gradient has dimensions of 1 over length. So, if my fundamental solution is 1 over r, if I take one gradient, I should get 1 over r square, take 2 gradients, I should get 1 over r cubed, and so on. Okay. So, those were the decaying harmonics, and we had also from the decaying harmonic solutions, I had also shown you how to get a series of growing harmonics. Okay. So, this was for n is equal to 1. The growing harmonic was just phi naught is equal to just a constant. Within a multiplicative constant is just 1. Okay. Similarly, phi 1, I am sorry, this is n is equal to 0. N is equal to 1 is xi, and for n is equal to 2 you get the next solution. Okay, so, let me just write it here. Is equal to delta I j r square minus 3 x I x j. Okay. So, in the growing harmonics, phi naught is just a constant, okay, just a constant temperature, of course, satisfies Laplace equation trivially. Phi 1 is a vector which increases proportional to r, because xi, right, xi is r cos theta for the z coordinate, r sin theta cos phi and r sin theta sin phi. Similarly, you can easily see that phi 2 increases proportional to r square. Okay. This was what we had discussed in the previous lecture. Hope you had an opportunity to revise it. Rather heavy going, but as you will see, it makes our subsequent calculations far more simpler. But there were two reasons why I went through this. One is the calculations that we do a little later will become far more simpler. The second really is to assign a physical interpretation to each of these harmonics. Okay. So, as we will see, we saw in the fundamentals of transport processes 1 that the first solution n is equal to 0 corresponds to a point source, where there is a net heat coming out of that point source. Okay. The first solution corresponds to a dipole, which is a source and a sink of equal strength. In the limit, as the distance between them goes to 0, but the dipole moment, the force, the source times the distance remains finite, you get a dipole. Okay. And so, we had drawn these figures in the previous lecture for a source. Okay. For a dipole, basically you get something that goes like this. The same as the dipoles in magnetic fields, as you recall. Okay. Then you have a quadrupole, which is 2 sources and 2 sinks. So, I have to have 2 sources and 2 sinks in such a way that the dipole moment is equal to 0. So, I will put red as the sources, I will put 2 sources in red and 2 sinks in blue. Okay. And the distance between these two have to be equal. Okay. So, let me just change this. And then you will end up with a field that looks something like this. Okay. It has a 4-fold symmetry. Okay, and so on, and so you have higher order terms. Okay. So, you have this with 4-fold symmetry, okay, and then you have higher order terms. So, these were the physical interpretations that we gave to all of these terms in this expansion. Similar physical interpretation holds for these spherical harmonic expansions here, the source and sink terms. Okay. And we will see that when we go through the momentum conservation equation, this physical interpretation will come in as a point force dipole, and so on. Okay. So, those are the physical interpretations of these terms, and we will see that a point force once again is like a point source. It gives a disturbance that goes as 1 over r. A dipole goes as 1 over r square, and so on. Okay. So, that is the reason that we went through this in some detail. The first is that we are dealing with these harmonics as vectors in themselves, without reference to r, theta or phi. Okay. So, that is one important point. Okay. And the other thing is that because we are dealing with vectors, we can easily get vector solutions to the equations, tensor solutions to the equations and so on. Good. So, one is that all solutions have to be linear in the spherical harmonics. Okay. So, I was trying to solve equations del square p is equal to 0 and del square for u I general is equal to 0. Okay. So, those were the two equations I was trying to solve. That means that both p and u I general have to be some linear combinations of these spherical harmonics. The spherical harmonics are complete and orthogonal. So, therefore, there is no projection of one spherical harmonic onto the other. Okay. Therefore, I have to have a linear combination which includes each one a constant times each spherical harmonic individually. Okay. You cannot have products of spherical harmonics in the expansion. So, that is one thing that I use. The solution can always be expanded in this series of spherical harmonic solutions. Okay. The other thing that I can use, as I emphasized 2 lectures ago, is that if I have a sphere moving with the velocity u, then the solution for both the velocity and the pressure have to be linear in u. Okay. So, if I multiply u by a factor of 2, the velocity and pressure at each point will also multiply by a factor of 2. If I reverse the direction of u, the velocity and pressure at each point within the fluid will also reverse. This sphere is spherically symmetric. Okay. So, if for example, the velocity direction were changed to this one, okay, if the sphere were moving in a velocity which was moving in this direction, right, the velocity of the fluid and pressure at each point should once again be linear in this vector u. Okay. So, I have to get a solution which is linear in the spherical harmonics as well as linear in this vector u, which is the direction in which the sphere is moving, okay, the velocity with which the sphere is moving. So, my pressure has to contain terms that are linear in u as well as linear in one of the spherical harmonics. Pressure is a scalar, u is a vector. The only way that I can get a pressure which is linear in u and linear in one of the spherical harmonics is to write this pressure as some constant times u dotted with a vector spherical harmonic. Okay. If I multiply this by a scalar, I will get a vector, and pressure is a scalar, so it cannot be a scalar. If I dot this with a second, third, higher order tensor, I will get something that is not a scalar. So, the only possible combination which was linear in u as well as linear in one of the spherical harmonics is this one, the vector u dotted with the first solution, the dipole solution. Okay. So, this is equal to A3 uj xj by r cubed, okay, because xj by r cubed is the first solution. Okay. Of course, the first solution can be taken either as plus xj by r cubed or minus xj by r cubed. Will not make a difference because that is only going to change the sign of A3 constant. Okay. The final solution which satisfies the boundary conditions will end up remaining the same regardless of whether I take this vector solution as plus xj by r cubed or minus xj by r cubed. Okay. Similar thing I need to do for the velocity, the general part of the velocity ui general. Okay. ui general is also linear in capital U, the vector capital U, and it is linear in one of the spherical harmonics. So, how do I write that? Okay. Okay. It has to be linear in U. Okay. One way to get it is by taking U itself and multiplying it by the scalar spherical harmonic. Okay. The scalar spherical harmonic is phi naught. Okay. So, this gives me a vector. I multiply u scalar by I multiply the vector u by a scalar to get a vector. I can also get this by dotting u with a second order tensor. Okay. If I take u and dot it with the second order tensor, I will get a velocity that is a vector. No further solutions are possible. I cannot dot it with a third order tensor, okay, because that would be a second order tensor, whereas my velocity is a vector, okay, similarly and so on. Okay. So, this is a complete solution. Okay. So, that is the dipole, I am sorry, that is the quadrupole spherical harmonic, okay, phi 2 I j. Okay. So, these are the complete solutions, and now I have to determine in these solutions the constants a 1, a 2 and a 3. Okay. I know that u I is equal to u I general plus 1 by 2 mu p times x I. Okay. This is equal to a 1 u I by r plus a 2 plus a 3 by 2 mu So, that is my complete solution for the velocity, in which I now have to determine the coefficients a 1, a 2 and a 3. Now, there are two things here. Okay. So, first of all, these coefficients can of course be determined from the boundary conditions, okay. But before I go on to the boundary conditions, I still have to make sure that the solution satisfies the incompressibility condition, that is that it has to satisfy partial u I by partial x I is equal to 0, the incompressibility condition. Okay. We have not yet satisfied that with this solution. Okay. So, partial u I by partial x I is equal to 0. Okay. So, I just take the divergence of the solution that I already have. Okay. There is one simplification that you can make here, okay, which I will briefly go through. Okay. You know that u I is equal to a 1 u I times phi naught plus a 2 u j times phi 2 I j plus a 3 by 2 mu x I times u j times phi 1 j. Okay. If I take the divergence of this, what I will get is that partial u I by partial x I is equal to a 1 u I partial phi naught by partial x I plus a 2 u j partial by partial x I of phi 2 I j plus a 3 by 2 mu. Okay. Now, I have two terms here which I have to use the chain rule for differentiation. Okay. So, let us just go through that. Okay. So, the first term is I take partial by partial x I of this one, of this x I there, partial x I by partial x I is just delta I. Okay. So, I will get u j phi 1 j plus x I u j partial phi 1 j by partial x I. Okay. This term is identically equal to 0. Okay. This term is identically equal to 0. The reason for that is as follows. Okay. We know that partial phi 2 I j by partial x I. Phi 2 is obtained by taking two derivatives, two gradients on the fundamental solution. So, this is equal to partial by partial x I of partial by partial x I of partial phi naught by partial x j. is obtained by taking two derivatives. Okay. And I can interchange the order of differentiation here to get partial by partial x j of del square phi naught. This is equal to 0 because phi naught is a solution of the Laplace equation. So, that term in the gradient of the in the divergence of the velocity field is identically equal to 0. And because of that I am basically left with the divergence of the other two terms. Okay. So, when I enforce the incompressibility condition, I can neglect this middle term in the expression for the divergence. Okay. So, this becomes a 1 u I into partial phi naught by partial x I is just phi 1 I, which is minus x I by r cubed. Okay. Phi naught is 1 over r. When I take the derivative of that, I get minus x I by r cubed, okay, plus a 3 by 2 mu into 3 u j phi 1 j plus x I u j into partial phi 1 j by partial x I is basically just, okay, so let us just work out partial phi 1 j by partial x I is just phi 2 I j. Okay. Phi 1 j is x I by r cubed. So, I will get delta I j by r cubed minus 3 x I x j by r power 5. Okay, delta I j by r cubed minus 3 x I x j by r power 5. Okay. So, this is minus a 1 u I x I by r cubed plus a 3 by 2 mu into 3 u j x j by r cubed plus x I times delta I j is just x j. Okay. So, in this I have the second term here, I have x I times delta I j, okay, which is just x j. So, I get plus u j x j by r cubed minus 3 x I square x j by r power 5. Okay. X I square x 1 square plus x 2 square plus x 3 square is just equal to r square. Okay. So, I have x I square by r power 5 is just 1 over r cubed, and because of that you can easily verify that these two terms will cancel out. Okay. And the other two terms are just minus a 1 u I x I by r cubed plus a 3 by 2 mu u j x j by r cubed. Okay. Both of them are u dot x by r cubed. Therefore, this basically tells me that if this is equal to 0, it implies that a 1 is equal to a 3 by 2 mu. Okay. So, the equation for the velocity field now becomes a 1 into u I by r plus x I x j u j by r cubed plus a 2 into a 2 u j into So, in this expression for the velocity field, I have just substituted that a 3 by 2 mu is equal to a 1 in order to satisfy the incompressibility condition. So, I get a 1 u I by r plus a 1 u j x I x j by r cubed plus the second term. Okay. So, that is the expression for the velocity field. I have two constants of integration still remaining, a 1 and a 2. Okay. Let us just write this in a slightly different form. Okay. There are two components here. One is proportional to u I or delta I j u j. the other is proportional to xi xj uj, that is x into x dot u. Okay. So, I have a1 by r plus a2 by r cubed plus uj xi xj into a1 by r cubed minus 3 a2 by r power 5. Okay. So, now this is the velocity field. Okay. It has two components. Okay. So, let me just write this out in a little more detail, so that it becomes clear to you. Okay. If I write this in vector form, this becomes u vector into a1 by r plus a2 by r cubed plus xi into uj xj is equal to x vector into u dot x. Okay, x vector into u dot x. Okay, so, there are two components, one which is along the u vector itself, the other which is along the x vector, because the I is on x. Okay. Enforce boundary conditions. Okay. So, this was my expression for the velocity, one component along u vector, the other component along the x vector. Okay. So, the boundary conditions on the surface of the sphere at r is equal to capital R, u is equal to capital U. Okay. That means that u has a component only along capital U vector. Okay. So, that if my capital U vector is in this direction, that means that at the surface of the sphere, the velocity has to be equal and only in the u direction. Okay, it is only along u, and it has to be equal everywhere on the surface of the sphere. Which is the x direction? The x direction is along the displacement vector. Okay. If I plot the x direction along the surface of the sphere, it will be along the displacement vector, okay, from the origin at various locations. Okay. So, that will be the x direction. Okay. The boundary condition requires that the velocity is only along u, because the sphere is moving only along that direction. That means that the component of the velocity along the x direction is identically equal to 0. Okay. There is no velocity component along the x direction. Okay. So, what that means is that this coefficient is equal to 1, because at r is equal to capital R, this coefficient is equal to 1 by r cubed is equal to 1, because that is the velocity along the x direction, and the other component has to be equal to 0. The velocity along the x direction has to be equal to 0, because the velocity is purely along the u direction only on the surface of the sphere. That is what the boundary conditions tell me. Okay. So, therefore, I should get a1 by r cubed minus 3 a2 by r power 5 is equal to 0. Okay. So, you can solve this and you will get a final solution as a1 is equal to 3 r by 4 and a2 is equal to r cubed by 4. Okay. You can easily verify that this solution a1 is equal to 3 r by 4 and a2 is equal to r cubed by 4 satisfies these two conditions. That is, at the surface of the sphere, the velocity is only along the u direction, component of velocity along the x direction is identically equal to 0. Okay. So, therefore, the velocity fluid velocity vector is equal to 3 r by 4 into ui by r plus uj xi xj by r cubed plus r cubed by 4 uj into delta ij by r cubed minus 3 xi xj by r power 5. So, that is my final solution for the velocity vector, and this velocity is at each point in the fluid. Okay. So, this gives me the complete velocity distribution at all points within the fluid. Okay. You can see that this velocity vector depends only upon u vector and x vector, not on their individual components. So, in that sense, this is far more general than the velocity that you would have got by trying to separate out the equation into 3 components and then writing down an equation for each component and so on. Okay. So, in that sense it is a very gentle solution. The other point, it contains 2 terms, one of which goes as 1 over r. Okay. Out of these, the first term is actually a source term. The first term is actually a source term which was there in the original solution for the general velocity. The second term actually comes out due to the pressure. Okay. Similarly, in the second term is actually a quadrupole term. It goes as 1 over r cubed. Okay. The pressure, which was equal to A3 uj xj by r cubed. Okay. If you go back and you look at what A3 was, it was equal to 2 mu times A1. Okay. So, this will be equal to 3 by 2 mu r uj xj by r cubed. Okay. So, that is the equation for the pressure. Okay. Now, this vector solution, of course, I mean, it is the solution of the equations, but it does not quite give you a physical insight into how the solution would look. Okay. So, let us take a little bit of time in order to look at the interpretation of this physical solution. Okay. Is equal to 3 r by 4 into plus r cubed by 4 we separate it out as usual into 2 components, one which is along u and the other which is along the x direction. Okay. So, this will be equal to ui into 3 r by 4 r plus r cubed by 4 r cubed plus uj xi xj into 3 r by 4 r cubed minus 3 r cubed by 4 r power 5. Just separating out the terms that are proportional to ui, which are these 2, and the terms that are proportional to xi xj uj, which are these 2. Okay. So, this if I write it in vector notation, I will get u vector is equal to u vector into 3 r by 4 r plus r cubed by 4 r cubed plus uj or x vector into u dot x into 3 r by 4 r cubed minus So, this now has 2 components, one the velocity which is along u vector and the second is the velocity along x vector. Okay. So, let us look at these 2 terms, the velocity along u vector and the second is the velocity along the x vector. Okay. So, let us take a sphere that is settling in a fluid. Okay. And let us assume that the velocity direction u is in this direction, the velocity direction u is in this direction. Okay. So, at the surface of the sphere itself, okay, the velocity is purely in the u direction. At the surface of the sphere itself, the velocity is along u direction alone. At r is equal to capital R, as you can see, the blue part goes to 0. Okay, at r is equal to capital R, the blue part is equal to 0, the red part is equal to just 1. However, if you are away from the sphere, from the surface of the sphere, you will have a non-zero due to the second blue part. Okay. The red part is of course positive everywhere. So, for example, at a location something like this, the red part is of course this way, it is going downward. The blue part is going along x vector, okay, x into u dot x. Okay. If u dot x is positive, if u and x are the angle between the two is less than 90 degrees, then you have a positive contribution along the x vector due to the blue term. Okay. And because of that, you will have a contribution due to the blue term that looks something like this. And therefore, your resultant velocity vector somewhere here will be in some resultant direction. Okay. When u dot x is identically equal to 0, that is along the 90 degrees, okay, you will have a velocity that is purely in the u direction, and so here the velocity will be only in the u direction. And now, when you go to a position on the downstream side of the sphere, okay, if you go to a position on the downstream side of the sphere, a position somewhere here, u vector is of course along the u direction itself. Okay. U vector is always in this direction. U dot x is negative, because the angle between u vector and x vector now is greater than 90 degrees. Okay. The angle between u vector and x vector here, this is the direction of u vector, x vector is in that direction. So, the angle is greater than 90 degrees. So, u dot x is negative. So, you have a velocity that is in this direction, because u dot x is negative. The net velocity is along the inward direction, and the resultant of these two gives me a velocity that looks something like this. Okay. So, if I plot it in terms of the velocity of the sphere, if I plot it in terms of the velocity of the sphere, okay, if I look at the fluid streamlines, what I will get is something like this. Okay. The solid sphere itself is moving at a constant velocity. So, the streamlines will all look something like this. Okay. On the upstream side of the sphere, you have the velocity going outward. And downstream, you have the velocity coming inward. So, that is the kind of velocity profile that you get due to the settling sphere as given by our solution of the Stokes equations. Okay. So, this is the velocity profile that we get. It is sort of clear, because as the sphere is moving downwards, this is in a fixed reference frame. As the sphere is traveling downwards, the velocity upstream has to go outward, because it has to push fluid out of the way so that the sphere can settle. Velocity downstream has to come inwards, because the space that is vacated by the sphere as it moves down has to be occupied by fluid coming inwards. Okay. And if you look near the sphere, you will get something that goes like this. Okay. So, this is the kind of velocity profile that you get in a fixed reference frame. Okay. If you were on the other hand in a moving reference frame that is moving with the sphere itself, right. So, you get the solution for the moving reference frame by subtracting out the velocity with which the sphere is moving. Okay. And if you work it out in a moving reference frame, you subtracted out the sphere velocity capital U. Okay. So, that the velocity of the sphere itself is a constant, I am sorry, the velocity of the sphere itself is 0. So, that the sphere itself is stationary. Okay. So, in that case, what has to happen is that the flow has to go around the sphere. Okay. The sphere itself is stationary and the fluid is moving upwards. Therefore, the flow has to go around the sphere like this. Okay. So, the velocity profiles look very different in a fixed and a moving reference frame. If you are moving with the sphere, fluid is going past you upwards, and therefore, you have fluid that is diverging as it goes past you. Whereas, if you are in a fixed reference frame, the space below the sphere has to get the fluid there has to be pushed out. So, it goes outwards. The space above the sphere, the fluid has to come inwards. Okay. All of that is captured by this solution, okay, of the equations. So, the velocity that I get is just by subtracting out u from this. If I subtract out u from this, okay. So, from this vector here, okay, from this vector here, the velocity of the sphere downwards looks something like this. Okay. So, if I sit at this point, I have a sphere velocity here which is less than u, because as you can see, when r is less than capital R, this coefficient is less than 1. Okay. When r is less than capital R, this coefficient here, I am sorry, when small r is greater than capital R, when you are outside the sphere, this coefficient is less than 1. Therefore, I have a larger velocity being added over here, and the net resultant that I get due to these three velocities will end up being something in this direction. Okay. So, it will be outward at the bottom of the sphere, and similarly if I subtract out this capital R over here, I will get a velocity that is inward behind. Okay, and that will give me this profile in a fixed reference frame. Okay. So, we have got the velocity profile, we have got the velocity, we have got the pressure. How do we calculate the force on the sphere? Okay. As you know, the net force is the integral of the force at each point on the surface. At each point on the surface, there is a stress that is exerted. The stress is equal to minus P delta Ij plus mu partial xi. Okay. For the present purposes, let me rewrite this a little bit, because my expression for the velocity has the index j in it. Okay. So, rather than using indices I and j, I will use the indices I and k, okay, for the stress. Okay, I will use the indices I and k. Okay. So, this is the stress acting at each point on the surface. Okay. Then you have this unit normal to the surface, okay, and k. Okay. So, the force acting at each point on the surface is equal to the stress dotted with the unit normal. Okay. So, therefore, the force acting is equal to T I k times N k. For this particular case, the unit normal is also equal to the displacement vector divided by its magnitude. Okay. So, since I fixed the origin at the center of the sphere, okay, so since I fixed the origin at the center of the sphere, the position vector anywhere on the surface is just x vector. Okay. The position vector anywhere on the surface is just x vector. Okay. Unit normal is x vector divided by its magnitude. The magnitude of the unit normal is x, is the radius r itself. Okay. So, this is just equal to T I k into x k by r, because x vector itself is the position vector of a point on the surface, that divided by its magnitude gives me the unit vector. That is the force exerted at each point on the surface. The total force F I is equal to integral of the force exerted on each point on the surface of T I k x k by r. Okay. So, now I have to evaluate T I k. For that I need the gradient of the velocity. Okay. I need the gradient of the velocity. I also need the pressure. Okay. So, let us write down the gradient of the velocity and the pressure. Okay. U I is equal to 3 r by 4 u j into delta j by r cubed plus x I x j by r power 5 plus r cubed by 4. Okay. So, now I have to evaluate partial u I by partial x k and partial u k by partial x I and minus p delta I k. Okay. Minus p delta I k is of course equal to minus delta I k into 3 by 2 mu u j x j by r cubed. So, that is not a problem, but I have to evaluate the gradients of the velocity fields. So, we will have to take the gradients of this velocity field. We will continue this in the next lecture. Gradients of the velocity field multiplied by the unit normal, integrated over the entire surface in order to get the total force acting on the surface of the sphere. So, the prediction of this total force, okay, as you probably know, this is given by Stokes law. we will be able to derive the Stokes Law solution by this method without reference to the individual components of the force, but rather just taking the vector velocity, the stress, integrating that to get the total force. So, kindly go through the derivation in this lecture and how we took the gradients and so on of the various vector and tensor quantities, and we will continue the evaluation of the total force in the next lecture from the velocity profile that we have obtained in detail in this case. Important to note that the velocity profile that we have obtained has been done without reference to the underlying coordinate system. So, this is most general, it can be used for any, it is obtained in terms of vectors, okay, and tensors, and that was facilitated because we managed to get vector and tensor solutions to the Laplace equations. So, kindly go through this. We will continue the evaluation of the force in the next lecture. We will see you then.